Good afternoon, all. So, welcome back to the third session on wheel mobile robots. I hope the course has been going well so far for whomever is attending the course. So, I hope you have gone through the lectures regarding week three. So, this is mostly about dynamics of wheel mobile robots, how to model a wheel mobile robot, how to model its equations of motion. In the lectures, we have basically covered two different kinds of methods to derive its equations of motion. We basically came across a method called Euler-Lagrange model. It's an energy-based method, and we have also come across the momentum-based method called the Newton-Euler method. And we have also seen how to map the dynamics equations of motion from the body frame to the inertial frame. And again, further to map the forces from the body fixed frame all the way to the torque available at the wheels. We have also seen how to do that for different configurations of wheel mobile robots. Here today for this session, just like what we have done in the previous two sessions, we'll just briefly summarize the important topics that is being covered through the lectures. And after that, we'll solve some questions, some typical questions that you could expect for your assignments. Okay, so getting on with the session, we'll simply cover what is meant by robot dynamics. So generally, dynamics is actually a broad term. It can cover, basically an umbrella term. So what essentially dynamics means? It's nothing but the study of systems that undergo changes of state as time evolves. So haven't discussed the importance of the time, how the dynamics actually changes with the time. We have only for this entire session, we have basically more focused on derivations of equations, only the modeling part. And if you have gone through the simulation lectures, the lectures where the professor simulates how a robot behaves, there we have basically it is also demonstrated how the system evolves with time. So this is basically a general description of dynamics. So specifically to robots, it basically studies the change of state. The change of state basically involves motion. So in robots, the change of state is basically how the robot moves as a result of the external forces and moments. And yeah, but basically dynamics is study of why and how motion occurs and when forces and moments are applied on the bodies. So like earlier in kinematics, we have only seen how a robot basically moves. It only deals with velocities and accelerations, but we don't really care about why these accelerations is introduced or how these accelerations are being introduced. So if a body has to change its state from of rest or a non-uniform motion, we all know that it has to be acted on a external force. And dynamics basically covers the effect of forces as well as moments on a rigid body. So why do we need to model a robot dynamically? So deriving the dynamic model of a robot is actually essential in the design, analysis, and control of a robotic system. So design in the sense like if you want to design a robot, be a mobile robot or in case of a robot manipulator, we may need to estimate how much forces or movements each of the joints are subjected to. Like if you want to design each and every links of the mechanism, we should know what would be the maximum loads that these links would be subjected on in order for us to design it safely so that it will withstand all sorts of possible loading. So that is where this design part comes in. And analysis. So analysis mostly means like how the system would respond. Like if you apply some sort of a force on all four wheels of a mobile robot, depending on the weight of the mobile robot and the inertia of the mobile robot, how the robot moves. In order for us to analyze that, we need to have a mathematical dynamic model of a robot so that we can basically predict or get some idea of its behavior. So that is where the analysis part comes in, and control of the system. So there could be multiple control objectives. For example, if you want the robot to track a specific trajectory, we have it should achieve at any instant of time, it should achieve the specific position, the specific velocity, and specific time. So there has to be, we have to make sure that the robot specifically follows the desired trajectory. And in order for us to do that, we have to design a controller so that it will basically predict what should be the input that is to be given at the next step. And yes, regarding the equations of motion, so basically the dynamic modeling of a robotic system or any mechanical system is essentially the derivation of their equations of motion. And depending on the degree of freedom of such systems, there will be equal number of equations of motion. So since we are dealing with uh, a mobile robot that has 3 degrees of freedom, we'll have 3 equations of freedom. And the procedure is like, once we go through the procedure, we'll simultaneously derive all 3 equations of motion, right? It's more or less similar to a spring mass damper system. You might know this, mx double dot plus bx dot plus kx equal to 0. So this is basically an equation of motion corresponding to a spring mass damper system. So in case of a mobile robot, we'll have 3 such equations of motion, which will predict its behavior, right? So the way in which the motion of a robotic system arises from torques or forces applied by the actuators and or from external forces, moments applied to the system. So the vector tau basically encompasses the actuator forces, the forces that we are supplying onto the system. It will also include external forces acting onto the system, maybe the external forces such as gravity, then payload, then all sort of other loads, maybe friction. Everything comes under this tau vector. And we need to correlate how these forces affect the motion of the robot. So this is basically a function of position. This is a vector actually, eta dot, a three-dimensional vector, eta dot, and eta double dot, right? So yeah, that is about equations of motion. And as you might have realized, there we have, just like in the case of kinematics, we have 2 different cases of sub-problems in dynamics. So similar to kinematics, we have something called a forward dynamics problem and an inverse dynamics problem, where in case of a forward dynamics problem, it's basically the estimation of the trajectory of the robot for a specified input vector input vector of torques or moments. So like it'll be simply like if you give some control inputs to the robot in terms of forces, how will the robot move? In terms how will the trajectory of the robot behave? So that is more or less about forward dynamics problem. So this is equivalent to simulating the robot or analyzing the robot. Simulating in the sense like if you want to give some forces, for example, if you give all equal wrenches or equal torques to all 4 motors, how would a differential drive robot moves? Right. So that is more or less about forward dynamics problem. You can easily correlate with forward kinematics as well. That is also equivalent to simulating or analyzing the robot in velocity level. So analogous to this inverse kinematics problem, we have this inverse dynamics. So if you want the robot to traject a desired trajectory, for example, if you want the robot to move a circular trajectory, so this is our desired trajectory defined by the position vector eta, the velocity vector eta dot, and the acceleration vector eta double dot. What should be the control input that we should be giving to all the 4 motors? Right? If this is how the robot should move, then what should be the torque vector or the input torques that we should be giving onto the motor? So such problems comes under the category called inverse dynamics problem. And this is equivalent to controlling the robot, right? I hope it makes sense because we want the robot to track a desired trajectory. What should be the input vector? So that is more or less controlling the robot. So yeah, that is more or less the forward dynamics and inverse dynamics problems. And yes, in order for us to model this, we have basically come across two different kinds of models, two different kinds of modeling methods. What we call this Euler-Lagrange method. That this is what we have seen as the first method in our lectures. So we basically can derive an equation of motion of a robotic system using this equation. Also, over your left-hand side is the vector of torques and moments. And the parameter here, the partial derivative of this scalar function, we call this as the Lagrangian of this specific mechanism. And zeta is basically the vector of degrees of freedom. So it could be the it's not necessarily the zeta that you have come across in kinematics. So in kinematics, zeta basically means UVR. So this is a velocity vector. But here we have a zeta that is somewhat different. It's not velocity. It's basically displacements. But degree of freedom coordinates along x b axis, the body frame axis, xb, yb, and zb. So zeta would consist of the velocity along the position displacement along x axis, the displacement along the y axis, and the rotation about z axis. And everything is represented with respect to the local body frame of reference, right? And what we have inside this parenthesis is dou L by dou zeta dot. And here over to your right hand side, this is dou L by dou zeta, right? So this zeta dot becomes a velocity, and if you further take the total derivative of this, we will get acceleration basically. And over here, you basically take the partial derivative of this Lagrangian with respect to zeta. So if you can able to find out the Lagrangian of any system, it does not have to be a robotic system. It can be any system. For example, it could be a spring mass system. So if you could determine the Lagrangian of any system, you can derive the equations of motion using this Euler-Lagrange formula, where this Lagrangian is nothing but the difference between the kinetic energy of the system and the potential energy of the system. And zeta is, as I have already mentioned, it's a vector of body frame coordinates or the body frame degree of freedom. And tau is the vector of input forces or moments. It's not exclusive to forces, it could be moments, depending on the degree of freedom that specific coordinate has, right? And if you, as you can recall, the mobile robot essentially lives within a plane. It does not move out of plane. So in that regard, you can fix the plane on which or the plane in which the robot is moving as a fixed datum. So in that regard, you can also since the plane in which the robot is moving is its own datum, you can consider the potential energy to be zero, right? So if the entire object or if the entire rigid body is living on the datum itself, you can fix the datum to be the 0 point, and you can consider the potential energy of that point to be zero. So in that regard, for this case of for this case of mobile robots, you can consider the potential energy to be zero. But that cannot be generalized for systems that lives out of plane, that has spatial coordinates. So yes, in this regard, we have also seen how to derive the kinetic expressions for kinetic energy of the system, right? So if you can recall over here, sticking to the convention that we are using throughout the course, we have a body fixed frame of reference over here called B, right? That is basically attached to the chassis of the robot. So that frame basically moves with the chassis of the robot. And the velocity, the linear velocity along this x coordinate is called u. And the linear velocity along the y coordinate is v. And the angular velocity along this z coordinate is, we denote it as r, right? And if the center of mass is at some other point, right, it need not be always be coincident with the frame of reference. It could be somewhere else. Because practically, we also need to consider the practical aspects also, because however perfectly you design, the center of gravity will be somewhat slightly offsetted from the geometrical centroid of your mobile robot. So if that is the case, then how will you define the kinetic and potential, the kinetic energy of the system? So as you can see with this diagram, the center of mass is displaced xb units from x-axis over here, and it's also displaced by yb units from yb units along y-axis. So the coordinates are basically xb and yb. So if those are the coordinates of point C, that is the coordinates of the center of mass, then what will be the velocity of point C? It is nothing but u, the contribution of this linear velocity u plus the contribution of this angular velocity, right? Equivalent to this r omega radius times omega, radius times angular velocity. And since the radius here would be yes, this would be ybc, and angular velocity is r, and the direction of this vector radius cross angular velocity would be this. That is why we have a minus sign over here, right? So this is ybc, this is uh, this is r, the contribution of r, sorry, this is ybc, and r would be trying to rotate this in counterclockwise direction. Then this term omega cross r or r cross omega would be in the negative x-axis. So that the total sum of vector would be u minus ybc times r. That will be its magnitude. And what will be the y component velocity of the point C? That will be v. This is v. Then what will be the component due to this angular velocity? R omega. That will be this distance xbc times r. So that component will be along this direction, because the angular velocity, since the angular velocity is in counterclockwise direction, the linear velocity contributed by this angular velocity r would be along the positive y-axis. So this vector would be r cross xbc. So that is what we have written over here, right? So the total kinetic energy would be simply but nothing but half m v square. V square is nothing but x c dot square plus y c dot square. So, and we also know the expressions for x c dot square and y c dot square. Plus, there is also another component of this kinetic energy due to this rotational component, that is nothing but the moment of inertia about the z-axis, that is out of plane, multiplied by the angular velocity, square of this angular velocity. So we is half I omega square, something equivalent to that. So this is our total kinetic energy, and we have basically established that the potential energy could be treated as zero, because we can consider this plane to be the datum plane itself, right? So how do you get the forces, the net forces along x-axis? So if you apply the Lagrange Euler-Lagrange formula, we have dou L by dou U. So if you take the partial derivative with respect to each of these coordinates, you will get the degree of freedom along x-axis, y-axis, and z-axis. So the first coordinate being u, our Euler-Lagrange formula would be dou L by dou U. This entire term again differentiated by d by dt, right? So if you substitute this expression onto this, and if you take the partial derivative of Lagrangian dou L by dou U, and again further take the derivative with respect to time, you will end up with this expression. That is nothing but fx. And similarly, if you do the same for the variable v or the coordinate v, you will get fy And what is the remaining coordinate? The remaining coordinate is nothing but this angular component r. So if you take the partial derivative of L with respect to r and further take its derivative with respect to time, you will end up with this big equation, right? And again, you will further have you will have some sort of a recurrence, because you will again, as you can see, you have this xbc dot term here. You will also have this ybc dot term here. So what you have to do is that you will have to substitute these terms, not this exactly. It'll be without these squares. You will have to again further substitute into wherever you find xbc and ybc, which would result in this final equations of motion. Fx would be so and so, Fy would be so and Mz would be so and so. And for any object moving with respect to a frame of reference, you should be familiar with what these components are basically called. So this u component is basically an acceleration along this u axis. We basically call this as slip acceleration. And VR, what is this VR? There is also a term for this. It's called Coriolis acceleration. Coriolis acceleration. And the remaining two terms are more or less familiar, because this is nothing but this is somewhat equivalent to uh, r omega square. But here this r is basically our angular velocity. So it's equivalent to this normal acceleration, normal component of acceleration. And the final term would be something equivalent to this r alpha. You might be familiar with this term. It's the tangential component. So basically, these are the contribution by the acceleration. So the forces are contributed by the slip acceleration, that is the linear acceleration along the corresponding axis, which is x-axis. Then you have something called the Coriolis acceleration, that is basically a product of linear velocity and angular velocity, v and r. And then you also have something called a normal acceleration along this axis and the tangential component of acceleration. And similarly for this Fy also, you will have the slip acceleration, which is v dot. This is the Coriolis acceleration. This is the normal component, and this is the tangential component. And correspondingly, you will also have the moment about this z axis. So like, I suppose, like, if you take the moment of each of these forces along with respect to this B frame, you will get this expression. Right? What are the moments caused by each of these accelerations with respect to this B frame? If you take the moments of each of these accelerations or each of these individual forces, you will end up with this big expression. Okay, so that is one aspect of this Euler-Lagrange equation. And sometimes you may also need to derive the same equations of motion using a more involved method called Newton-Euler method. And then you may also ask, why do you need two different kinds of methods? So it does not make much of a difference in mobile robots, but in case of a robotic manipulator, it will basically make a huge difference, because Euler-Lagrange method mostly maps this external forces directly to actuator forces. Give one more example. We'll have, yes, the trajectory of the robot is directly mapped to actuators, external forces, and so forth. So it's basically a direct mapping between the desired trajectory to the actuators and external forces. Whereas in case if you derive an equation of motion using or Newton-Euler method, it is more comprehensive, such that you will have to do this propagation from each and every joints, starting from the tip of the robot, the working tip of the robot, or this end effector, all the way to the base frame. So with that regard, you will also determine the reaction forces available at each and every joint. So that could be essential if you're trying to design the links of the robot, so that you can estimate the maximum forces each of these links are subjected to. So, but in case of a mobile robot, you don't have that many links. You basically essentially have a rigid body, and you only need to figure out what are the forces acting along UV and R axis. There aren't any intermediate rigid bodies, coming into play in case of a mobile robot. But in case of manipulators, the scenario is basically different. So anyway, like you can still define, or you can still derive this Newton-Euler method without much of a hassle, because it's more systematic in case of a mobile robot. So essentially, what you have over here is it's more or less similar to the earlier diagram that we have seen for the Euler-Lagrange method. And similarly, we also have the body fixed frame rigidly attached at the geometrical center of the platform. And we also have the center of mass, or the center of gravity of the robot, somewhere which is a bit offset from the centroid by a distance xbc, right, with respect to this vertical y-axis, and ybc with respect to this horizontal x-axis. And if you take the component of all the accelerations acting at this point, this is nothing but accelerations along the y-axis and acceleration along z-axis, and you also have a reactive moment contributed by this alpha cs. Alpha cs is nothing but the rate of change of rotation. That is nothing but r naught. So if that is the case, then how would you derive this equations of motion? It's not, it may seem difficult at first, but when you think about it, it's not really that difficult, because you are only taking the derivative of vectors, position vectors. If you take the derivative of position vectors, you will get velocities. If you further take velocities, you will get accelerations. So the easiest method, it's pretty much straightforward. It may look complicated at first. So over here, what I'm drawing is nothing but the inertial frame of reference, which is going to be always fixed with respect to the ground, xi and yi. And over here, you have the body frame of reference at the geometrical center of the robot. And you also have the center of mass. So if I use vectors connecting each of these 3 points, how would that look like? So if this is one vector, if I call this vector as P, it basically denotes the position of point. So this vector is position of the point B with respect to frame I, right? And this vector would be the position of the point C, the center of mass, with respect to frame B. And from here to here, from the coordinate C all the way to the point A, this is nothing but the position of C with respect to I. So how would you write this vector expression? So this vector from inertial frame of reference to the body frame, the frame C, is nothing but the sum of these two vectors. So vectorially, you can easily write it something like this. The position vector of B with respect to the position vector of C with respect to I is position vector of B with respect to I plus position vector of C with respect to B pre-multiplied by the rotation vector of B with respect to I. Right? I hope this is clear enough. And if you would like to have a recall of the notation that we are using, the top superscripts over here that we are representing denotes with respect to which frame of reference we are writing this expression. Right? And the bottom frame is what we are referring to. So here, P of C with respect to I, it's self-explanatory. We are defining the position of point C, right, with respect to frame I. So that is what this expression is. And this expression is the position vector of frame B, right, with respect to frame I. And this entire term is this vector, uh, position vector of C from B represented in frame I, right? So like since this is a body fixed frame, this vector will always be fixed with respect to this frame because this frame and this point are basically part of the same rigid body. And as a result, there won't be any change of this vector with respect to this frame. But there is obviously going to be a change between this vector and this vector. So if you, in order for us to maintain homogeneity, everything will have to be represented with respect to a same frame of reference. So that is why we are using this rotation matrix. So this is nothing but the rotation of B with respect to I. So this is nothing but the position of point C with respect to I. So we have only reached until position. We need to go all the way to acceleration. So how do we do that? You can differentiate this equation. So differentiating, right? How would that look like? So derivative of P with respect to Ci is derivative of P with respect B with respect to I plus we can use the chain rule for this term. So how will that look like? It will be IRB V P dot C plus IRB dot BPC. Right? I hope this expression is clear enough. It's nothing but we are only differentiating this expression with respect to time. And if you take a look at each of these terms individually, what do you think about this term? This is the derivative of the position of point C with respect to frame B. So like as I've said earlier, since point C and point B are part of the same rigid body, there won't be any relative change between the position coordinate of point C with respect to frame B. So in that regard, the derivative of uh, the position vector or the position of C with respect to B is always going to be zero when expressed in the frame of reference B. So this term is always going to be zero. You can ignore this term from now onwards, right? If that is the case, then you can rewrite this expression as, uh, yeah, the derivative is I P dot B plus I R B dot B P C. So I'll just put this under a box, right? And again, we may also have a term that is not very familiar to us. This is the derivative of a rotation matrix. So what essentially does that mean? So yeah, so that is also again another topic. If you are interested, you can basically refer to any textbooks on rigid body dynamics. So any textbooks on rigid body dynamics basically discusses about rotation matrices and how the rotation matrix change with respect to time. So if you are interested, I can give you a brief overview of that. So just for reference only, I'll quickly write this down. So you basically know R is an orthogonal matrix, right? So R is nothing but an orthogonal matrix. For example, cos theta minus sine theta 0, sine theta cos theta 0, 0, 0, 1. This is an orthonormal matrix because if you multiply, if you take its transpose is also its inverse, and the magnitude of each of these columns, the norm of each of these columns is 1, right? This will be cos square theta plus sine square theta, that is 1. This is sine square theta plus cos square theta, that is also 1. And this is also, the magnitude is also 1. So since it is an orthonormal matrix, you can always write it as R multiplied by R transpose is identity matrix, right? Because R transpose and R inverse are essentially the same. So you can write it in this way. So if you take the derivative of this equation, it will be, if you take the derivative of this expression using product rule, it will be nothing like R dot R transpose plus R dot transpose. This will be 0 because derivative of an identity matrix that is nothing but a constant is 0. So again, if you further rewrite this, you can also rewrite this as R dot R transpose. Then this second term, you can also rewrite it as R dot R transpose, the whole transpose equal to 0, right? You can write this term, sorry, you can basically write this term like this, right? Because if you expand this transpose, it will be, this is nothing but A, B, the whole transpose. It will be like B transpose, A transpose. So if you expand this, it will be like, if you expand this R dot and R transpose, the whole transpose, it will be like it will be like R dot transpose. That is nothing but this term that we have already written here. So we have a matrix here, R dot R transpose, and we also have the same matrix, R dot R transpose, the whole transpose. This is 0. So when will that happen? So if a matrix and if the sum of a matrix and its transpose is 0, fundamentally we should know that this matrix should be a skew-symmetric matrix, because only a skew-symmetric matrix has its sum plus its transpose, sum of the skew-symmetric matrix plus its transpose to be 0, right? So that is it can only happen with the skew symmetric matrix. So we basically know, we basically establish that R dot R transpose is a skew symmetric matrix, right? So just to quickly demonstrate that what I'm talking about, so we'll take a simplified rotation matrix actually. So because in mobile robots, we are only dealing with the simple rotation matrix about Z axis. But in a general case, we can have rotations about all the 3 axes. But for the time being, we are only focusing on a rotation matrix about Z axis. So it will be cos theta, the familiar form, minus sine theta, 0, sine theta, cos theta, 0, 0, 0, 1. So what will be, this is the rotation matrix about Z axis, right? So what will be the derivative? What will be R dot? R dot would be, if you take a derivative of each and every term within this matrix, R dot would be minus sine theta. So this entire term would be multiplied by theta dot, because cos theta, derivative of cos theta with respect to time is minus sine theta multiplied by theta dot, right? Okay, I'll write it for each of these metrics, minus sine theta, theta dot. So derivative of minus sine theta is minus cos theta, theta dot. This is 0. Then cos theta, theta dot minus sine theta, theta dot 0. And the third entry would be 0, 0, 0. Right? So this is nothing but R dot. So what happens if you multiply this R dot with this R transpose? You will end up with the skew symmetric matrix as we have proved. So if you take the multiplication of R dot and R transpose, this is nothing but R dot R transpose would be minus sine theta theta dot minus cos theta theta dot 0 uh, cos theta theta dot minus sine theta theta dot 0 0 0 0. This multiplied by the rotation matrix itself, not the rotation matrix, the transpose of the rotation matrix. So that will be nothing but cos theta minus sine theta 0 sine theta cos theta 0 0 0 1. So if you multiply this together, you will end up with, I'm not showing the individual term by term multiplication. It will be like 0 minus theta dot 0 theta dot 0 0 0 0 0. So this is your skew symmetric matrix over here, right? And this is of a general form 0 0 omega z, right? Omega z is basically nothing but the angular velocity about the z axis. So 0 0 theta dot, and all the diagonal terms would be 0, just like in the case of a yes, just like in the case of any general skew symmetric matrix. So going back to the previous expression, we are interested to find what this R dot is. So over here we have R dot R transpose as this matrix over here. Then what will be R dot? So if you take this to this other side, if you multiply this with R, okay, so R dot R transpose is S. So R dot R transpose whole inverse will be S times R transpose the whole inverse. So what will that be? So the yes, so this term is nothing but see, R transpose and R inverse are essentially the same because that is nothing but an orthonormal matrix. So this term would be an identity matrix, right? This term would be nothing but an identity matrix. So you can cancel this out. So R dot would be S times R transpose whole inverse. So this will be nothing but S times R, right? So S is basically a skew symmetric matrix of omega Z. So R dot is basically a skew symmetric matrix multiplied by R. This is also equivalent to omega cross R, right? For example, if you have two vector, maybe two vectors, if you want to take a cross product, you can basically write this cross product as a matrix operation. I hope you are familiar with that. So if you have two vectors, omega I cap plus omega 1 I cap, omega 2 j cap plus omega 3 k cap, then R1 I cap plus R2 j cap plus R3 k cap. You can do this normal cross product operation using determinants, or you could do this as a matrix multiplication operation, similar to this operation. So if you express this omega as a matrix, a skew symmetric matrix, which that will be nothing but 0, 0, 0, minus omega 1, omega 2, omega, sorry. If you do this operation, 0, 0, 0, omega 1 minus omega 2, omega 3, this is minus omega 3, omega 2, this is minus omega 1. This multiplied by this vector R1, R2, R3, you will still end up with the same cross product operation. So the point being, if you write this, this is nothing but equivalent to omega cross R. So R dot is this skew symmetric matrix S dot R, where the skew symmetric matrix is this one, where this will be 0, 0, omega is it. That is how the skew symmetric matrix would look like. And all the diagonal entries would be 0. Again, like if you would like to further read onto this, you can refer to any rigid body dynamics textbook. Okay, so yeah, I hope we haven't ventured too deep off topic. We can get back to our derivation. So the only point to be remembered is R dot is the skew symmetric matrix S. So since its components are angular velocities, we can basically call it as omega. A skew symmetric matrix omega. R dot is the skew symmetric matrix omega force multiplied by the rotation matrix R. Or you could write it as omega cross R. Both are essentially stable because cross product, you can rewrite the cross product as a matrix multiplication operation. So yeah, further expanding this, it is derivative of the position vector C with respect to I would be position vector of B with respect to I plus omega of angular velocity of frame B with respect to I, because we know that this body frame would be rotating, the mobile robot would be rotating with respect to this inertial frame of reference. This cross, we also have this term, R dot will be omega cross R. We also have this term R. In this context, it will be the rotation matrix of body frame with respect to the inertial frame. Then we'll also have this term, the position vector of C with respect to B. And you can again further rewrite. So what exactly is this term? This is nothing but velocity of frame B. So velocity of frame B expressed in frame I. So this is IPC dot. This is velocity plus. Okay, so just for further convenience, I am basically re-multiplying the second term with the rotation matrix. Watch carefully what I am doing. I omega B cross IRB BPC. So what I've done is that I've simply rewritten this equation over here. The only change is that I have pre-multiplied here over here before this omega term, these two terms, right? This is nothing but R and R transpose, right? The only difference is we are only flipping these indices. So R and R transpose, simply pre-multiplying, it does not make any difference because R transpose is nothing but identity matrix. So even if you are doing this, there is not going to be much difference. So the reason is that we can take this IRB common for all the terms. So again, like since we would like to model everything with respect to the body frame of reference, as you know, because everything was represented with respect to the body frame of reference. Like we have U with respect to body frame of reference, we have B with respect to body frame of reference. So everything was defined with respect to body frame of reference. So in that regard, we can also define this vector with respect to body frame of reference. How do you do that? So the velocity of point B with respect to I is nothing but velocity of point B that is expressed with respect to B multiplied by the rotation matrix I R, sorry, yeah, RBI. right? So this term is equivalent to this, right? Velocity of B represented with respect to I is nothing but velocity of B represented in its own frame of reference, then pre-multiplied by the rotation matrix that maps it to the initial frame of reference. So if I replace this term with this, I'll end up with this expression IRB BPB, right? And if the vector is represented with respect to its own frame of reference, then we don't need to have this superscript. It is understood. We ignore or we omit this superscript and we'll simply keep this term BB as such. And with that, we can simply take everything. This IRB is common for all these terms. IRB is common here. IRB is common here. IRB is also common here. So if you take this IRB common, this will be, if I take this out common, IRB, we have VB over here plus. So if you take this term outside, because IRB is common, you have this thing, angular velocity of B represented with respect to I. Then we also have it pre-multiplied by rotation matrix of I that is referred with respect to B. So this is R transpose. So this entire term would make it omega B referred with respect to B itself, right? Angular velocity of B referred with respect to B. So you can also, just like we did in the case of this linear velocity, you can write it as omega B itself. Here it was with respect to I, and due to the fact that we have a pre-multiplication of rotation matrix here, it will be omega B matrix with respect to B. And you can represent it simply like omega B. So that will be omega B cross position vector of C with respect to B. So yes. So this is your expression for velocity. I'll label this as 2. This is nothing but velocities. And again, further, you have to take the derivative of equation 2 one more time to get the accelerations. Accelerations of point C referred with respect to I. So if you are still following, I can show you that. I'll basically show you that term. So it's again not that difficult because you only need to apply the product rule here. You know, you can consider this to be the first term and you can consider this to be the second term. And if you apply the product rule, it is nothing but the acceleration of point C with respect to I is nothing but. So I'm taking the product rule. So I'll keep this rotation matrix as constant. So I'll take the derivative of the terms inside the bracket, BB dot plus omega B dot cross position vector. And again, there is also, since there are two more terms here, we also have to take one more product rule, that is omega B cross BPC dot. Then the second term, IRB dot VB plus omega B cross BPC. And just like what we have remarked in the previous slide, this term is 0 because the relative position of C with respect to B is not going to change because they are part of the same rigid body. So this term is always going to be 0. So you can disregard that. And you also know what this is going to be, the derivative of the rotation matrix. So this is nothing but omega B, I omega B cross IRB. Because we have seen this earlier. What is the derivative of the rotation matrix? So taking everything into consideration, we can write this as IRB multiplied by VB dot plus omega B dot cross BPC, and this term is 0, so we don't have to write it. And we have to replace this with the appropriate expression, that is plus I omega B cross. There is also going to be an IRB. Then within that bracket, we have VB plus omega B cross BPC, right? And just like what we have done in the previous case, I am simply pre-multiplying this term over here by this RR transpose. Because if you do that, there is nothing is going to change because RR transpose is identity matrix. So IRB, then BRI with the indices flipped. So that means both are basically transpose. So for all these terms, if I take this IRB as constant, there is an IRB for this term. There is also an IRB for this term. So if I take IRB common, IRB, so we have this term over here inside this bracket, velocity of B, derivative of velocity of B represented with respect to its own frame of reference. So that is nothing but acceleration, right? Acceleration of point B referred with respect to its own frame of reference. Then what are the remaining terms? We have omega B. We also don't have any superscript here. So that means omega B is referred with respect to its own local frame of reference B. And omega B dot, derivative of omega B dot is angular acceleration, alpha B, right? So this is alpha B cross VPC, right? So this is what I have written so far. So we cannot still close this bracket. We have the second term also. So from this term, if I take this IRB outside, we have this term basically. So that is nothing but omega B referred with respect to its own frame, this term. So in effect, we'll have plus omega B cross VB plus omega B cross omega B cross BPC. So essentially, this is nothing but acceleration of point C with respect to inertial frame of reference. So again, this is not the final step. We still need to refer everything with respect to the body's frame of reference, right? So everything is the MACX and MACY. ACX and ACY are all referred with respect to its body frame of reference. But here, everything is referenced with respect to inertial frame of reference. So we are still a single step away from that. So how do you do that? We need to express everything with respect to the body frame of reference. So again, if I pre-multiply this term with R transpose, nothing is going to change. And I can easily do that because if I do that, IRB, then BRI, nothing is going to change because R transpose is nothing but yes, it's nothing but identity matrix. And if I take this term here, what will we end up? What is it that we are going to end up with here, this side? So if I take this term over here, so if you consider this as R, when it goes to this side, it will be R inverse or R transpose. And this is also R. So if you introduce this R to this side, this R and this R transpose will get cancelled. So you can cancel out, it will cancel out this term. And what you end up here is this term actually, the acceleration of point C referred with respect to point I, then you are basically pre-multiplying with R transpose. So it will transpose everything from inertial frame of reference to body frame of reference. So in effect, you will end up with acceleration of C, right? Acceleration of C represented in frame B. This is nothing but acceleration of B. 1 second. I'm now mostly out of battery. Yes. Okay. Acceleration of B plus angular acceleration of B cross the position vector C with respect to B, plus we have this Coriolis term omega B cross VB, plus we also have this normal component omega B cross BPC, right? So this will be our final expression for acceleration because this is a vector. So a vector, since it's a vector, it comprises of this term ACX and ACY, right? So acceleration of C with respect to B in a planar case, because we are only dealing with a planar mobile robot. So we don't consider the spatial coordinates. So if you simply consider the planar coordinates, we'll end up with ACX, ACY, and the third coordinate acceleration of z-axis is 0 because we are not considering spatial acceleration along z. Yes, then what are the other terms? We have taken care of this term. What about this alpha term? Alpha B would be nothing but 0, 0, r dot, right? Because we are not considering angular acceleration about x-axis, not considering about y-axis, only considering about z-axis. And we know that the angular velocity of z-axis about z-axis is r, and alpha being its derivative would be r dot. Then what about this term, BPC? Position vector of P, position vector P of C with respect to B is nothing but these terms over here in this diagram, XBC and YBC. So it will be XBC, YBC is 0. Then what about this term? Omega B. We all know what omega B is. Omega B is 0, 0, R, right? Then we also know what this term is, VB. VB is nothing but U, V, and 0, all the linear components of velocities. So what you do is if you substitute everything, you can essentially get the component-wise equations of motion. Like so, 1 second. Yeah, so if you substitute each and every component, so if you multiply this with mass, you have this acceleration component with respect to frame. This is basically a vector. So if you multiply this with the mass, center of mass, you will get the component-wise components, the component-wise equations of motion. So this being the first equation, and yeah, this entire term be the first equation, and this term being the second equation, and this being the moment equation about the z-axis. So again, this is nothing but like if you take the moment of MACX, MACY, and the moment contributed by this term, so all the moments about this point, you can actually, and if you substitute this ACY and ACX from this final vector, what we have derived here, right? The first two components of this vector will give you the Fx and Fy. And if you take the moments of this MACX, MACY, and this ICZ, alpha CZ about the frame of reference, body frame of reference, you will end up with the third equation. And this is essentially the same thing, exactly the same thing you derived using the Newton-Euler method, sorry, the Euler-Lagrange method, the energy-based method. And you can also compactly define this entire equations of motion using this vector and matrix approach, where this vector tau is fx, fy, and mz, and this matrix D is what we have over here. This is a mass matrix, and zeta dot is the derivative of velocity vector. So u dot, v dot are accelerations, and r dot is the angular acceleration. And over here, this is a vector of centrifugal plus Coriolis terms. So over here, we have identified which are the Coriolis term and which is the centrifugal term. And this vector is basically it comprises both the Coriolis as well as the centrifugal terms. And if you have observed, you can also see that this mass matrix D is also symmetric. So D transpose is also D. It's a positively definite matrix. It's also a symmetric matrix, right? And yeah, that is also what we have covered in this lecture. And further, there is also another thing that I would like to point out. We have so far defined this entire equations of motion in terms of body frame of reference, right? If you can recall this diagram, the forces here acting along x-axis fx, this one fy, and the moment about this axis, everything is represented with respect to the body frame of reference, which is rigidly attached to the chassis of the robot. So you can also define, just like how we map the velocities from the body frame to the fixed frame, you can also do a similar kind of mapping uh, of the torques or all the forces from body frame to the fixed frame. So how do you do that? You can basically do that by through the, it's basically nothing but conservation of power. So it states the power consumed at the inertial frame is equivalent to the power consumed at the body frame of reference. So it does not matter which coordinates you are defining the dynamics, the power is basically the same. And also you also know that power is nothing but the dot product of force or torque and velocity, right? This is basically, power is a scalar quantity. It's nothing but dot product of force and velocity, right? And you can basically represent the dot product using this matrix and vector operations. So tau transpose eta dot. So this is the power in inertial frame of reference, and this is in body frame of reference. So the subscript eta basically denotes body frame of reference. And you know what this eta dot vector is. Eta dot is x dot, y dot, and psi dot. If you can recall from the kinematics lectures. And zeta is the velocity vector u, v, r. And this is with respect to the inertial frame. And zeta is referred with respect to the body frame of reference. Right? So our intention is to map between tau transpose and tau. So what you have done is you have derived these equations of motion in terms of tau, in terms of body frame. And if you want to find out the torques in terms of inertial frame of reference, how do you do that? So you also know from kinematics, how do you map the velocities from the body frame of reference to the inertial frame of reference using this Jacobian transformation. So if you substitute, if I label this as equation 1, and if I label this as equation 2, and if you substitute equation, equation 2 onto 1, right? So 2 in 1 would basically yield tau eta transpose eta is tau transpose. Instead of zeta, I'll write it as I'll write it as J of psi inverse eta dot, right? So you can basically cancel these eta dot terms. So tau eta transpose is tau transpose J of psi transpose. So basically I'm writing this inverse as transpose itself, because this J of psi is nothing but the rotational matrix, and in case of rotational matrix, since it is orthonormal, its transpose is also its inverse. So if I take the transpose of this one more time, tau eta is J of psi times tau. I suppose I'm right in doing this. Yes, I'll just label this. Right, so I'll label this as equation 3. So just like in the case before, if you have derived the torque vector in body frame, if you want to convert it into the inertial frame, you simply pre-multiply it with the Jacobian matrix, or in fact here in the case, the rotation matrix, right? So we have essentially derived tau. Tau would be this form, this inertia matrix times theta dot. Then plus we also have this vector of Coriolis and centrifugal acceleration. So I label this as equation 4. And yes, so from equation 2, we basically know for a fact that eta dot is J of psi times theta. So if I take the derivative of this term, we have a theta dot term here, and here we only have the theta term. So if you want to get the theta dot term, we have to take the derivative of equation 2. So to do that, what we'll do? Eta double dot would be J dot. I'm ignoring the bracket for the time being. J dot theta plus J theta dot. So from here, what will be theta dot? Theta dot will be eta double dot minus J dot theta, the whole pre-multiplied by J inverse. So I'm labeling this as equation 5. Right? So if I substitute this equation 5 onto this equation, right? 5 in 4. So 5 in 4 would yield tau as d multiplied by this term over here. That'll be J inverse eta double dot minus J dot theta plus this term over here, n of theta. So if I further expand this bracket, it will be tau is nothing but d multiplied by J inverse eta double dot minus dj inverse J dot zeta plus n of theta. Right? And we also know the mapping between this vector tau and this vector tau eta. Right? So what will be tau? I can write tau as, if I pre-multiply the inverse or transpose of this vector here to this side, what will you get? You will get tau. So I can replace this by this expression, J inverse tau n. Sorry, tau n. So then what will be your tau n? what will be tau n. So you have to pre-multiply the inverse of it here. So again, if it in that case, if that is the case you are doing, then it will be nothing but j d j inverse eta double dot. This is nothing but tau eta minus j d j inverse j dot theta plus j of n theta. And here, this is tau eta. You can call this vector as the new inertia matrix because the coefficient of eta double dot would be your inertia matrix. You can call this as your new inertia matrix, d eta, eta double dot. Plus, you can basically call this entire term as the new Coriolis term, n of eta, right? So again, basically, this will be your equations of motion in inertial frame of reference. Equations of motion in inertial frame of reference. Just like in the case of the body fixed frame of reference, you can also see that this is also going to be a positive definite symmetric matrix, right? And some and again, like if you call this as d of eta, you can also see that the same term also appears here. So you can also call this as d of eta. If you call this as d of eta, you can also call this as d of eta, right? So I'll just mark it just to understand. So this entire term over here, that is, sorry, mark with a different ink. This entire term is what I'm labeling as d of theta, and this term on its entirety is this vector n of eta. So this is equations of motion in inertial frame of reference, right? And as you can see, it's more or less convenient to derive everything in body frame of reference and transpose it back to the inertial frame of reference if it is necessary. And yeah, so far we are only dealing with the forces and moments about a frame of reference, right? If it was everything was derived with respect to body frame of reference, and we have also seen how it will look like if we derive everything, if we transpose everything back to the inertial frame of reference. So the coordinates we are dealing with until now are fx, fy, and mz. And that too mostly are the forces along xb and yb axis and the moment about zb axis. And just like how we mapped this UVR to the angular velocities of the wheel, we would like to map these vectors of forces and moments to the actuation inputs, the torque supplied to each of these wheels, or the forces supplied to each of the wheels. So as you can see, the configuration of a robot changes depending on what structure you are adopting to. So you will also need one more further transformation. And as you can see, this is going to be much simpler than what we did for kinematics, because kinematics, you have a W matrix which maps UVR to omega 1, omega 2, omega 3, etc. And this is only this is nothing but a simple vector decomposition problem. So if you have fx along this direction, the wheels can only contribute forces along its longitudinal direction, along the direction of its rolling. So if this is F1, the force is traction force contributed by wheel 1, and F2 is basically the traction force contributed by wheel 2, then F1 plus F2 is nothing but Fx, right? So that is what this expression is. And what about F5? What are the forces in y direction? So that is essentially zero because these wheels effectively, we consider conventional wheels to provide infinite accelerations along lateral direction. So it'll be the resistance would be infinite. So there won't be it will not be capable of executing any maneuvers or any forces, exerting any forces along the lateral direction. So we consider the forces along lateral direction to be zero. And if you resolve the moments about this z-axis, if you consider the distance between the two wheels to be 2d, F1 will contribute to a clockwise moment. So that is why we have, sorry, uh, yeah, I think this is inverted. This should be F2 minus F1, right? Because F1, if F1 is along this direction and your rotation center is here, it will contribute a clockwise moment, and F2 will contribute a counterclockwise moment. So it will be the moment about moment about this axis is it would be minus F1d plus F2d. So if you write all these expression into a vector and matrix form, this is what you would get over here. This expression is what you get. So if you are able to determine what are these parameters, you can easily find out. You can easily map or easily find out what this F1 and F2 are. Or conversely, the opposite is also true. If you know what F1 and F2 are, you can determine what are the forces exerted at Fx, Fy, and Fz. And with that, you can also determine how the robot moves. And similarly, in the case of an omni-wheel robot, it also has forces exerted along this direction because this is the axle of the wheel, and these are the rollers. So the rollers axis are along these lines, and forces exerted by wheel one would be along this direction, positive force. Forces exerted along wheel two would be along this axis, and same for wheel three. And if you resolve all the forces along x, y, and moments about z-axis, you will end up with this equation: F1 cos phi1 plus F1 cos phi2 plus F1 cos phi3. So that is the net forces on x-axis. And you can also easily see that what these phi1, phi2, phi3 are. Phi1 is 90 degree. Phi2 is 90 degree plus 120 degree, that is 210. And phi3 is 210 plus 120, that is 330 degrees. So phi1 is 90, phi2 is 210, phi3 is 330. And the y component is, if you simply replace this cos by sine, you will get the y components. And the moment is this F1 times the perpendicular distance L, F2 times perpendicular distance L, and F3 times perpendicular distance L. And since all the moments are contributing to a counterclockwise rotation, all the moments are positive as well. So this is how your dynamic wheel configuration matrix for an omni wheel will look like. And one more case for the tricycled wheel. In case of a tricycle-like wheel, you have a powered and a steerable wheel. So the wheel will exert a tractive force along this axis, along the longitudinal axis F1, and theta can be controlled using a steering axis. So theta as well as the F1 both are controllable in case of a tricycle configuration. So again, with that, if you further resolve F1 onto XY and the moment about z-axis, you will end up with Fx is F1 cos theta 1 and Fy, because since these passive rollers exert infinite resistance over the lateral direction, however force F1 exerts, it cannot contribute to any traction along Y. So we consider Fy to be 0. And what is the moment about z-axis? So if you resolve F1 along parallel and perpendicular components, this will be F1 cos theta. This will be F1 sin theta. And F1 cos theta and the center of rotation coincide. So there will not be any component of moment from F1 cos theta. And F1 sin theta will make it rotate counterclockwise because the moment arm here is L. So the moment about its axis will be F1 sin theta multiplied by L. So again, writing it as a matrix and vector form, it will yield you this expression. And finally, one more thing, you also have the mechanism wheel. So just like what we did the last time, we have the forces act along this direction. If you consider this as phi1, and this will be, if this will be F2, you can consider this to be phi2. This will be phi3, and this will be phi4. And the cosine component of all the forces will lead you Fx. The sine component will lead you to Fy. And if you take the moments, like you have to resolve the forces along parallel and perpendicular components. And each of these components, parallel as well as perpendicular component, will exert moments about the body fixed frame of reference. So that is why we have two moment terms for each of the forces. So F1 has two moment terms, F2 has two moment terms, F3 has two moment terms, and F4 has two moment terms.
Excuse me, sir.
Hello?
Sir, excuse me.
Yes.
In this slide, you are showing a Fy force, a
Yeah.
component Y. But in the
Hmm.
previous slide, though
Yeah.
there is a component, why it was not put? Just one before this slide.
Okay, this one.
Yeah, here you see that
Yes.
red color wheel. If you take
Hmm.
the component,
Yeah.
F1 sin theta will come there, but it is
Yes.
put as 0.
Yeah, the reason we put is that because even if there is a force, there will be a force. Definitely F1 will exert some force,
But it
but
will move.
it will not move because these wheels will basically exert infinite resistance over the lateral direction.
This
So no
matrix,
matter what amount of force these exert, this will exert opposite to that, infinitely larger forces opposite to whatever this F1 is.
this
So that will
matrix
be essentially, sorry.
This matrix is useful for us to calculate the displacements. That's why we are not considering.
No, not necessarily displacements. It's only to calculate Fx, Fy, and Mz. That's all.
Okay.
Yeah, displacement was when we considered kinematics. That was in the last lecture. If
Okay.
you were there in the last section or week 2 lectures. But here, this is only to consider the forces.
Okay.
How whatever forces is exerted by this steerable wheel, an opposite amount of infinite resistance will be offered by these passive conventional wheels.
Okay.
So it won't have any component along. But in case of a mechanism wheel, this robot can actually, because of the rollers, it can move in any direction. It can move
Yeah.
vertically up, vertically down, side to side, diagonals. All sort of motions are possible in case of a mechanism wheel.
Okay, sir. Thank
So
you.
yeah, further, if you substitute all the values, if you substitute like corresponding phi1 and phi2 values. So if you recall the lectures, it will be plus 45, minus 45, and so forth. And the coordinate of this wheel would be this is 2L and this is 2D. So coordinates of this will be plus L plus D. This will be minus L plus D, and so forth. So if you substitute all the correct coordinates and correct angles, you will end up with this expression, this coordinate, this configuration matrix in dynamic level. Yeah, so it's only a matter of force resolution. And yeah, we'll also wind up the session with some sample questions, maybe 10 or 11 questions, more or less similar to what you can expect for your class assignments. So yeah, the first is basically a true or false questions. Uh, so for a given trajectory, for a given desired trajectory, finding the required input vector torque is known as forward dynamics. So if you have a robot and if you supply the desired trajectory, eta, eta dot, eta double dot, and it will give you the control input. So is this a case of forward dynamic problem or is it a case of an inverse dynamic problem? Can anyone answer this? It's inverse. Yes. Ajay Krishnan has said this is inverse. So in that regard, this is an inverse problem. So yes, I think two of you have responded it to be an inverse problem. So in that regard, you can easily conclude that the answer is indeed false because the question says forward, the answer is indeed inverse. So the correct answer is false. So if you check the solution, it is indeed false, right? So we can move on to the second question. So the Lagrangian, what we have derived in the Lagrangian Euler-Lagrange method, what exactly is this Lagrangian? Is it kinetic energy plus potential energy, kinetic energy minus potential energy? It's Ke minus Pe. Yes, Ke minus Pe. And in case of mobile robot, we have basically neglected the potential energy. But yes, choice two, correct. But if you design manipulators, because the principle is still the same for robot manipulators, but in robot manipulators, the potential energy will become an important factor. You cannot ignore or you cannot neglect PE for manipulators, just like how we did in case of wheel mobile robots. So
Sir,
again, that is indeed, yeah, sorry.
what does a higher value of Lagrangian mean, or a less value of Lagrangian mean?
Uh, a less value of Lagrangian means it's not that intuitive to uh, see what it means. A less value could mean the energy change between Ke and Pe is less. So in that case, the robot or the mobile robot could be moving very slowly, or it is uh, it is only lifting a very small payload. It could be moving very slowly. All these things could be all these things could be could be could come under how a small Lagrangian uh, you know can denote, right? So like if a robot is not moving that high, if a robotic arm is only moving a very small distance at a that too with a very small height, that can mean a very low Lagrangian. So if it is lifting a huge load and if it is moving with a high rate of change of velocities with a very high acceleration, that could obviously mean it can have a high Lagrangian. And
Okay.
if you take the derivative, you will also get higher forces also. Yeah. So again, it's also very straightforward. It's indeed Lagrangian. Okay, so moving on to question 3, it says we have a differential wheel mobile robot, right? So if anyone needs, I can basically reproduce this image. If I take a screenshot, okay, I'll take this vector. I'll take this because we may need this to solve the problem. Okay, copy. Yeah, this was question 3. So the question says, for a given differential wheel mobile robot, if the first wheel is generating a traction force of 1 Newton. So if you can recall, this is the chassis, this is x-axis, this is the y-axis. And by convention, we choose this wheel along this x-axis to be wheel 1. And we choose this to be wheel 2. And the traction force along wheel 1 is F1, that is given as 1 Newton. And traction force along wheel 2. F2 is given as 2 newtons actually, as per the question. Then what will be the forward and lateral direction forces? So if you resolve, yes, if you resolve everything along x-axis, sigma fx is f1 plus f2. That is nothing but 1 plus 2. This is 3 newtons, right? And since this is a differential wheel robot, there will not be any forces. Fy is going to be 0 because there won't be any motion or there won't be any traction along y-axis because of the infinite resistance contributed by the conventional wheels. So Fy is 0, Fx is 3 newtons. Okay. Okay, so Ajay has solved this earlier. 3 Newton longitudinal, 0 Newton lateral. Right? I hope again that is also clear with that. Yeah, so the option is indeed 3 Newton longitudinal, 0 Newton lateral. So yeah, moving on. Again, it is a problem of differential wheel robot. In a differential wheel drive robot, if the first wheel is generating a traction force of 1 Newton and the second wheel is also generating a traction force of 2 Newtons, then what will be the vehicle's motion? Again, the scenario is still the same. The forces are still the same. Uh, we need to find how the robot is going to move. So if you determine what Fx, Fy, and Mz are, we can get an idea about how the robot is going to move. And if you take a look at here, we haven't been given D. The value of D is not given. So we'll take any random value. It's not a problem. So 1, 0, sorry. 1, 1, 0, 0 minus D, D, 1, 2. Because F1 is given as 1 Newton and F2 is given as 2 Newtons. So if you multiply this out, you will get 3, 0 minus D plus 2D, that is D. So Fx is, this is nothing but Fx, Fy, Mz. So there is a component of force along x-axis and there is also a positive component along z-axis, the positive rotation component about z-axis. So the robot can move like this, right? Starting from here, it will move in a counterclockwise direction. Gradually, it will move to counterclockwise direction. So in that regard, what is the correct option? I think option C is given by Kamalkar. So everyone basically agrees as option C, I think. Move forward and rotate counterclockwise direction. Yes, that is indeed 3. So yeah, it's also an easy question. Okay, so similarly, it's also exactly more or less similar to how we did last week for uh, kinematics. So here, this is a problem for mechanism wheel, and this time you are also given the configuration matrix, right? So in this exams also, you can expect configuration metrics for configurations such as mechanism wheel. You can also expect it for omni wheel. But for differential drive robot, mostly we won't provide this configuration metrics because it's so simple you can derive instantly, as you solve the problem. So yeah, for given mechanism wheel drive, the wheel configuration matrix at dynamic level can be expressed as so and so. And if the vehicle needs to move in a lateral direction towards left along positive y-axis, then what would be the individual wheel forces? So just like how we did, you need to find out the right combination of F1, F2, F3, F4 so that you will get an appropriate Fx, Fy, Mz belt. So if you would like to have the screenshot of mechanism wheel robot, I can take this and reproduce this to the question over maybe here. Yes.
Sir, the configuration matrix given in this week and the earlier week both looks the same. Is that true?
Not necessarily. It may not be necessarily. So, like if you take a look at the previous week's uh,
There
lectures,
there is A and D values are there.
yeah. It's all different actually. It's not the same. And here, if you have observed, we have basically changed the uh, direction of the rollers
Oh, okay.
here, right? Earlier, it was in kinematics, the rollers were this roller was here and this roller was here. So we have swapped the position.
Okay.
And like depending upon what kind of what the rollers, how the rollers are aligned, you may get different matrices. And the configuration matrix for forces as well as velocities are different. There are different units actually. And if you can recall this, in case of velocities, the final entries of the final term would be 1 by L minus D or something like that. Not L minus D. It was 1 by something, 1 by L minus D or 1 by D minus L. So the units will also be different. Okay, so again, the procedure is still same. You need to find out the right combination of F1, F2, F3, F4. And can anyone tell what will be how would F1, Fx, Fy, and Mz would look like for this specific problem? Fx, Fy, Mz. It should look something like since it says it should move towards left, so, along positive y-axis. So positive y-axis is this axis. So Fx, Fy, Mz should be something like 0, k, 0. So the robot should move strictly along y-axis. It should not have any component along x-axis. It should also not rotate about its axis. So the third component is also 0. The only positive component would be uh, about y-axis. So GP has said it's minus 110. How can it be minus 110? It should be, it says it should strictly move along y-axis, right? Should be strictly along y-axis. So it should look like 0, 0, 1, 0, right? Yeah. So if it were indeed like you suggested, minus 1, 1, 0, it will have a component along negative x-axis and it will have a positive y-axis. So it will move diagonally like this. But as per the question, we want it to move like this. So Fx, Fy, Mz should look something like 0, k0. And you need to find the right combination of F1, F2, F3, F4 so that you will be able to get this vector, right? So Ajay says it's F minus F, F minus F. Is that correct answer? Can anyone verify that? F minus F, F minus F. So if I reproduce this here, 1 by root 2. So I'll just ignore 1 by root 2 because it's just a constant. So 1, 1, 1, 1, 1 minus 1, 1 minus 1.
You can also ignore L minus, take out L minus D and put 1, 1, minus 1, minus 1.
1, 1, minus 1, minus 1. Yeah, that is also correct. So Ajay says it's F minus F, F minus F. So if you multiply this out, it will be plus F, plus F, plus F minus F. This is 0. Second term would be plus F, plus F, plus F, plus F. So this will be 4F. Third component will be plus F, minus F, minus F, plus F. So this is also 0. Yeah, so that is indeed correct. So which of this option is correct? Option, yeah, D, I guess. Option 4. So if you cannot strictly follow, strictly quickly calculate this, you can, you can basically eliminate few of the obvious choices. Obviously this is not going to be true because if all are driven forward, it will only move forward. So you can eliminate this, and this is f minus f. So one wheels along one side will rotate along one direction. So that corresponds to pure rotation. We cannot be sure about the direction though, but this is corresponding to a pure rotation. So you can also eliminate this option. And another option is this option minus f plus f minus f. So that is a potential candidate. This option 3 is a potential candidate. Option 4 is also a potential candidate. Option 5, minus f plus f plus f. That also corresponds to a pure rotation. And option 6 is everything is minus f minus f minus f minus f. So that can only move in this direction. So you can also eliminate this option. So yeah, the potential options are only options 3 and 4. So if you are still unsure, you can eliminate all the obvious choices and start with these options and see which of the options gives you the correct answer. That way you can solve these kinds of problems. So yes, option 4 was indeed the correct answer. So question 6. This is again a problem of mechanical wheel robot. And if the wheel need to rotate clockwise direction in its own position, then what will be the wheel forces? Yeah, so it should be a pure rotation. So how should fx fy mz look like? And it also says clockwise direction. So please be mindful of the rotation also, the sense of rotation. So fx fy mz should look something like 0, 0. Is it plus k or minus k? Since it is clockwise, it should be minus k. Because rotation about minus z axis would be the clockwise rotation. And again, you can use this elimination method. Which of these options would you eliminate first? First option you can eliminate. Second option, ff minus f minus f. That seems like a good candidate. Third option, minus f plus f minus f plus f. You can eliminate that because that does not seem to be a candidate of pure rotation. Fourth question, f minus f minus f. You can also eliminate that. Fifth option seems like a potential candidate because it is minus f plus f plus f. And the final option, minus f minus f minus f minus f. You can also eliminate that option as well.
John, just a comment.
Yes.
I have put all this into Excel sheet.
Uh-huh.
What I am seeing is whatever potential movement they are asking, only
Yeah.
that one is getting a value, and all others are getting zeros.
All the others are getting zeros.
Yeah, and that means you have written 0, 0, minus k, right?
Yes.
Or clockwise. So when I look
Yes.
at the matrix,
Uh-huh.
the first option is giving me
Yes.
positive longitudinal direction. Second
Okay.
option is giving me
Yes.
anti-clockwise direction. Third option is giving me negative longitudinal lateral direction.
Okay.
Fourth option is giving me positive lateral direction.
Okay.
Option is giving me anti-clockwise movement.
Fifth
And
is clockwise or anti-clockwise?
-4 I got.
You got -4. Okay. So that is clockwise only, right? Minus
Right.
something is
Minus is clockwise. Okay.
clockwise. Okay.
And
Yes.
the last option is giving me a negative lateral longitudinal direction.
Okay. Okay.
So
So
what I
yes.
am trying to convey is when they
Yeah.
asked us to find out which one is the clockwise.
Yes.
So I need to check the third row multiplied with these choices and see whether
Mhm.
it is not zero.
Yes. Correct.
So I don't have to do the full multiplication. Just take where we are going to get a number for the given
Uh-huh.
option and
Okay.
identify that row and just
Uh-huh.
multiply with the given options.
Okay. There is also a potential danger in that. Because if you were there in the last lecture, we also considered a case where a robot moves diagonally, right?
Right, right. Okay,
Did you get the point?
right.
So
Okay,
if it moves diagonally, the final entry would still be zero, and the top two entries would be non-zero,
okay,
right? So in the exam, if the options for diagonal movement comes, and you only solve for the third final entry, you may end up making a mistake,
right. Okay,
right? So that could be a potential trap if in this exam if you get that kind of options.
it will take a lot of time to check all these options unless we have a
Yeah,
methodology.
but if you can easily eliminate, so you don't have
Right.
to check, you don't have to plug in all these options one by one.
Okay,
See, like just I have said here, you can easily eliminate these options. So you can eliminate one, you can eliminate two, you can eliminate these two options. You only need to verify whether this or this is true. You only need to mostly verify two options. All the
okay,
other options you can actually discard, because obviously if all the forces are going in one direction, it's only going to move along that direction, right? If it is all F, it is only going to move in longitudinal direction. So you don't even need to consider that. If the
okay,
problem is asking for a pure rotation, you don't need to consider these options. You don't need to
okay,
consider this option, this option, this option. You don't need to consider any of these options.
okay. I understand.
Yeah, yeah, yeah. Okay.
Yes, sir.
So yeah, that is indeed option. So what you said is correct actually. This is indeed correct. This is indeed the clockwise answer. And yeah, this is a numerical problem. So the inertia matrix of a mobile robot with respect to the body frame is given as so and so. And if the vehicle is oriented at 60 degrees with respect to this inertia frame, what is the inertia matrix with respect to the inertial frame? So there is a lot of inertia terms. You could easily get confused. So you have D matrix. You are also given the orientation between the body frame. This is inertial frame, and you also have the body frame of reference. And these are oriented at 60 degrees apart. So this much information is given. So if D matrix is given in body frame, what will be the D matrix in inertia frame? So we have basically uh, discussed the transposition of matrices in from body frame to inertia frame. So if you can recall, I'll simply write this expression. If you wish to further go back to the derivation, you can find the recording of this lecture and go back, or you can still go back to the NPTEL lecture videos of the professor. And yeah, so the inertia matrix or the mass matrix in inertial frame of reference is J inverse transpose D J inverse, sorry, J transpose. Or this is equivalent to J D J transpose. Both are equivalent actually, J D direct. Because J is an orthogonal matrix. So if you take inverse and transpose, both are essentially the same. J inverse and J transpose are essentially the same. So you also know the J because it says 60 degrees, it's aligned 60 degrees. So J would be nothing but cos 60 minus sine 60, cos 60, then 0, 0, 0, 0, 1, right? And transpose is you only need to transpose it as simple as that. So yeah, if you substitute the numerical values onto this expression or this expression, whichever be this case, you will end up with one of the correct answers. So have you solved this? If has anyone tried with MATLAB or Excel, or should I simply give the answer, or you can check it later?
We'll check it later, sir.
Okay, so the option is indeed B. right? Yeah. Because like if you go back to the lectures, you will find out how to correlate between the mass matrix in inertial frame of reference and body fixed frame of reference. So the answer is indeed going to be option B. Yeah, and again, these are all similar problems, right? So earlier we considered clockwise rotation. Now it's asking counterclockwise rotation. So you only need to flip whatever we said, whatever we actually considered in the previous case, you only need to flip directions. So I guess what was the options? I think for rotations, this option and this option were the potential candidate. And you have established this as clockwise rotation, and you have established this as counterclockwise rotation. Right? And the question specifically asks counterclockwise. Right? So I'm not fully solving the specifics. I'm just giving out these answers. It's going to be option B. Because now you want this F matrix to be 0, 0, K. Earlier it was minus K, now you want K. So you have to find out the correct combination of the source vector so that you will get this Fx, Fy, Mz vector as 0, 0, K. Yeah, so that is indeed the correct choice. Option 9. So until now we have only considered mechanism wheel drive. This is for omni wheel drive, right? And the question asks is if the vehicle need to move it negative right toward lateral direction. So if this is the chassis of the mobile robot, and if this is the body fixed frame, this is Y, this is X, and the robot should move in the negative lateral direction, negative Y axis. Sorry. If that is the case, then how should this Fx, Fy, Mz vector, how should it look like? Fx, Fy, Mz should look like 0 minus k 0, right? So 0 coordinates along fx axis, 0 coordinates along z axis, and minus k along fy axis. It should only move in the lateral negative axis. So yeah, 0 minus 1, 0. So in that regard, what is the correct option? What will give you the correct choice? I think it should be either of this, either option E or option F. Minus 2f, f, f. So Ajay has said it's minus 2f, f, f, and f. Is that correct? So you only need to simply plug this expression here and see whether you will get fx, fy, mz as this one. So if you get it, then you can you can finalize that answer to be the correct choice. So yeah, since we have covered enough problems of the same type in kinematics as well, we don't need to solve it, I guess. So the correct option is option, yeah, option F, the final option. And question 10 is also, yeah, if the vehicle needs to rotate in clockwise direction, then the individual wheel forces should be, yeah, this is actually very straightforward. In case of a mechanism wheel drive, if all the wheels are rotating in one direction, if all the wheels are rotating at equal magnitude in a single direction, then it will rotate. But whether it should rotate, but what is the correct direction? Is it plus f plus f plus f, or is it minus f minus f minus f? Which of the options could be correct? And it says clockwise rotation. It is indeed minus f minus f minus f. Yes. But this can be easily solved for omni wheels. But in case of a mechanical wheel, you always have to check because depending on the type of rollers, axis of rollers, it can it can be counterintuitive. So whatever you think intuitively, it could be sometimes it could be the opposite. So yeah, this is indeed minus f minus f minus f. We don't have to delve further onto that. Yeah, so this is the final question. So yeah, if the question basically says if the vector of applied forces and torque with respect to the body frame of reference is given as 537. So the vector tau is given as 537, right? And okay, then the question asks, then what is the vector of applied forces and moments with respect to the inertial frame of reference? So you need to find tau eta in inertial frame of reference. And it also says consider at this instance the axis of the frame B is at 30 degrees with respect to the x-axis of frame I in the counterclockwise direction. So if this is your inertial frame of reference, this is x, this is y, xi, yi, and this is the body frame of reference attached onto the chassis of the mobile robot, xb, yb, and the orientation is 30 degrees. Sorry, 30 degrees. So, like from the conservation of power, we have basically discussed the mapping between tau and tau eta. And what was that? If you can recall, I think tau is J transpose tau eta, right? And you have been given tau, you need to find tau eta. How will you find that? So if you pre-multiply LHS and RHS with J inverse transpose tau, this would be tau eta. And here J inverse transpose is similar to taking inverse twice or transpose twice, because inverse and transpose are basically same for an orthonormal matrix. And what is this J? J is cos 30 minus sine 30, sine 30, cos 30, then 0, 0, 1, 0, 0. So yeah, since it is equivalent to taking the inverse twice or transpose twice, you can basically write this as J of tau itself. Still similar, right? So if you do that, you will get the answer to be, I think, option B, I suppose. I think. Yes. Yeah. Okay, so you can expect similar questions. And maybe from the theory part, also you can expect a few questions, regarding conservation of power. If you may be given different vectors on different frames, and converting mass metrics from one frame, one reference to another reference, from body frame to inertial frame, and yeah, more or less similar problems to what we have solved here. And you may also need to identify, sometimes you may be given the terms of the equations of motion, and you may need to identify which of the terms corresponds to the Coriolis term of the equation of motion, which terms corresponds to the normal component of the equations of motion. So similar questions, from the theory part, right? Yeah, so yeah, that'll be it. I think we have basically covered few relevant questions regarding week 3, right? So yeah, if there is, I don't have any further points to discuss for regarding week 3. Yeah. So if any one of you have any doubts, you can ask me now. Otherwise, we'll wrap up the session.
Sir, I have a request for you.
Okay.
I saw your YouTube channel, and
Uh-huh.
looks like you are taking this session second time. Last year,
Yes.
so you only have taken it. So
Yes. Yes. Yes.
since you have developed a lot of expertise in this field, and over a period of 2 years, you might have
Yeah.
watched relevant videos on YouTube.
Okay.
Like the
Uh,
reason I'm telling is when I first saw that Magnum
uh-huh.
wheel, I was thinking, how does this work? And I went into
Okay.
YouTube and I saw a video by a Lessix channel. They have
Less
clearly
six. Yes. Yes. Yes.
showed,
Yes. Yes.
they have clearly showed how the force resolution works and all those things. And
Okay. Yes.
I liked that video a lot.
Uh-huh.
So since these videos are coming into your channel and maybe the content of the current lecture, NPTEL may be responsible. But whatever other videos, I feel you can
Mhm.
create a playlist and
Yeah.
say my personal wheeled robotics and put them there so that any
Mhm.
in future any student who is watching this, it will help them. Otherwise,
Yeah,
unless
because it'll be interesting. But the thing is that I am only doing this for the purposes of NPTEL, and my area of work is not on mobile robots.
okay, okay,
So at the moment, I work on cable actuated manipulators,
okay.
and like I cannot add anything further from what we are currently discussing as part of this NPTEL course, because
Yeah,
like they have strict instructions on on just to limit the topics about what can we say about what
okay,
is
okay,
being covered on the lectures.
okay, okay.
But I agree with your suggestion, because at the moment it looks very boring, because if someone is interested in that topic and if someone visits my channel, it looks completely boring, because we are only limiting everything with respect to the questions or whatever is discussed in the
So
lectures.
what I am telling is you put a
Yeah.
playlist there, but never
Uh,
mention about that in the class.
okay,
You,
okay, okay, okay.
you
Yes.
you are not going to promote that playlist. You
Okay,
are
okay,
doing it
understood.
for your own interest. It's up to you.
Yes.
Okay.
Yes, yes. Okay, I'll take that actually. It's a good suggestion actually.
You will
Yes,
never put the that playlist. If someone comes and visits your channel, they'll find it. Otherwise,
they can actually find it actually. Yes, yes, yes. I really appreciate that suggestion actually. I'll see if I can do something about it. Yeah.
okay. And I have
Okay.
a second question which I
Yeah.
cannot understand. I have posted it in a what is called forum. It was
Okay,
related
but I
to
couldn't see any messages actually until now.
it was yeah, it was posted in the first week itself. Second
Okay.
question you have answered. First question was not
Uh-huh.
answered. Still, when it was green, it is regarding mobility. When there are green wheels, we are putting it as one mobility degree of mobility is one. But when it is two red wheels, we are putting the
Uh-huh.
mobility as a two. Is it that each individual wheel can be switched on and off by the user? That's the reason why we have a two degree of mobility.
Yes. If there are two red wheels, then each of these two red wheels are driven by individual motors.
Yeah, individually they can be controlled. That's the reason why
Yes.
mobility is two. Two.
Yes.
Oh, okay, okay. Now,
That is the reason why the mobility is two, because mobility is nothing but a degree of maneuverability plus degree of steerability.
okay,
And like, for example, if this is the robot that you're talking about, a differential wheel robot, this is the example that you're considering,
right.
differential wheel robot. This is X, this is Y. And yeah, if you consider these to be the red colored wheels, each of these wheels are driven independently.
Okay.
See, otherwise, how can we control? How can we say this is omega one and this is omega two? We cannot say, right? If both are controlled by same motors, both of these wheels can only move in a constant speed. So it can only go forward and backward. So if you want to make the robot rotate, each of the angular velocities need to be controlled independently, omega one and omega two separately. So we have two motors, right? So we have mobility as 1 plus 1, that is 2. Steerability is 0. because we don't have any steering axis. It is a fixed axis wheel, so steerability is zero. So as a result, this maneuverability will be mobility plus steerability, that is 2, right? But I couldn't see your question actually. I'm not sure. Maybe
First week, it was in first week.
first week
Before,
itself.
yeah, before the
Okay.
question, what you call, please upload the videos into YouTube. Before that question, I have put that.
Okay. Let me check that actually. Your name is still
Mulakar Babanpalli.
Kamalkar. Okay. But okay, I'll check the
No
discussion
problem.
forums with
Now,
this. Yeah. Okay. Yeah. Okay. Yeah.
is there any prior course requirement for this course?
No, nothing. You only need elementary linear algebra. Nothing else you need to require. But
Because
the thing is, like the most involved topic that we have considered for this week is the derivation of this the Newton-Euler equations of motion. Right? So we have written a lot of vector equations. We have also taken the derivative of vectors and all those things. So for that, you may need some background in rigid body dynamics or
okay,
rigid body mechanics. But it is not even necessary because rigid body dynamics mostly covers motion of rigid bodies in 3D. But here we are restricting everything on a plane.
okay,
And I think it's always the best source to identify or to learn about, derivatives of vectors in a moving frame of reference and derivatives or rotation metrics is always any standard textbooks on rigid body dynamics. So there you will find, how to take derivative of a vector that is moving on a frame of reference. So all sort of interesting things comes into that picture. If you are
unless
interested in, yeah, if you are interested in derivation of equations of motion.
there are a lot of numerical problems hand
Yeah.
involved. I am not in a position to understand all those
Yeah, yeah,
equations.
yeah. Because it's not really necessary because you only need to follow what is being taught in the live lectures, and the derivation
No,
is
I'm not talking about
systematic.
this course. I'm not talking about this course. In general,
Ah,
when there is
in
a
general, yeah,
theory being discussed, unless they
yeah,
give a lot of numerical problems and their solutions are available, their
yeah.
solutions are available, I can go forward, backward, switch bit, and then I'll develop an understanding. I was wondering
Ah.
how you developed such an understanding at the age of 30. And to take a lecture of this, it requires at least 20 years of experience. That's what my
Uh-huh.
understanding is. I appreciate your efforts.
Okay. Like anyway, like I've been working in this domains since like I'm actually a PhD scholar, so I've been working here since maybe 3-4 years actually. So if you are also working on something that is that involved, it might not be that difficult actually. Because
Okay.
sometimes when you have to, if you have to come into, sometimes you need to understand the fundamental basics of some problems. Then only you will, able to crack some of the difficulties that you may face. So that is why I can do this because I do this all the time. For any not for mobile robots, but most of the systems. And while you derive, you may encounter a lot of problems, and you keep on wondering, why did that happen? Why did that happen? So you have to, come back to the fundamentals more often. So
Okay.
yeah, just for the purposes of this course, that is not at all necessary. But if you're working or if you are designing something, coming back to the basics is always you will always get back to the basics because that'll become like a necessity actually.
Thanks a lot, sir.
Okay,
Have a
thank you very much. Yeah. Okay, so good luck with the assignments. So if there is nothing else, I am winding up the session. Okay, so thank you for joining. See you next week. Okay.